In our world, speed is everything. We expect to find anything we're looking for instantly, right? But how do computers actually do that? How do they sift through millions, even billions of items so fast? Well, the secret isn't just about raw power. It's about smart organization. And we're about to look at one of the most brilliant tools ever invented for the job.
But here's a wild idea for you. What if the very thing you did to make your data perfectly organized was the one thing that could make your super fast search tool slow to a crawl? It sounds completely backwards, doesn't it? But this paradox is a real classic problem in computer science, and figuring it out is key to building things that are not just fast, but reliably fast.
So, to solve this problem of searching for things quickly, we got this incredible data structure called the binary search tree, or BST for short. You can think of it as the original hero of our story, a tool designed for one thing and one thing only, finding data at lightning speed.
So what exactly is a binary search tree? It's a tree-like structure that follows one simple but incredibly powerful rule. For any spot you pick in the tree, we call it a node. Everything to its left has a smaller value, and everything to its right has a larger value. That's it. This one little rule is the entire secret to its speed.
And the beauty of this is just how simple it is. You just have to remember, left is less, right is more. This golden rule applies everywhere at every single node in the entire tree. It's this incredibly consistent order that lets us search so fast. All right, let's see it in action. Let's say you're looking for the number 40. You start at the very top, the root. Let's say the root is 50. Is 40 smaller or larger than 50? It's smaller, right? So we immediately go left. Now maybe we're at a node with the number 30. Is 40 smaller or larger than 30? It's larger. So we go right. And boom, there it is. See what happened? With every single choice, we threw away half of the remaining data. It's just ridiculously efficient.
Seems perfect, doesn't it? It's fast, it's elegant, it's simple. But our hero has a hidden flaw, a kind of Achilles heel that can be triggered under one very specific and surprisingly common condition. This is where our story takes a dark turn, and where perfect order can actually create total chaos.
So we have to ask the critical question. We've seen how great the tree is with random data, but what happens if we feed it data that's already perfectly sorted? Like if we insert the numbers 10, then 20, then 30, then 40, one after the other in perfect ascending order. And this is where the problem just slaps you in the face. In the best case scenario, when you insert data randomly, you get this beautiful, bushy, balanced tree. It's wide and it's shallow, which is exactly what makes it so fast to search. But in the worst case, with that sorted data, the tree degenerates into this long, pathetic, skinny chain. It's not really a tree at all anymore. It's just a glorified list. And the performance difference is just staggering. A nice balanced tree gives you what we call O log n performance. Think of it like looking up a word in a dictionary. You just jump right to the section you need. But that skewed tree, its performance degrades to ON. That's like trying to find that same word by starting at the letter A and reading every single entry until you finally get there. It's a catastrophic failure. So our original hero is deeply flawed. But don't worry, because a new hero is about to step onto the scene, the AVL tree. It's a genius evolution of the BST, and it was designed specifically to make sure that worst-case scenario can never, ever happen. Okay, so an AVL tree is still a binary search tree at its core. It still follows that left is less, right is more rule. But it adds this one crucial superpower. It is self-balancing. It is constantly checking itself to make sure that for any given node, the height of its left side and its right side are never more than one level apart. So how in the world does it do that? Well, it uses a really simple calculation called the balance factor. For every single node, it's constantly checking the height of its left branch versus its right branch. And the result of that check has to stay within a very strict range. A balance factor of +1? Totally okay. That just means the left side of a node is one level deeper than the right. It's a little lopsided, sure, but it's stable and completely within the rules. A balance factor of 0 is, of course, the dream. That's perfect balance. It means the left and right sides below a node are perfectly symmetrical, exactly the same heights. This is what the tree is always trying to achieve. And a balance factor of -1 is also allowed. It just means the right side is one level deeper. So the only acceptable values are -1, 0, and +1. The second that number hits +2 or -2, alarm bells start ringing. The tree knows it's out of balance,
and it has to do something about it right now. So what is that something? What is this immediate action it takes when things get out of whack? The answer is a really clever maneuver called a rotation. You can think of it like this. Every single time you add a new number, the AVL tree checks the balance factor of the nodes all the way back up the path you took. If it finds any node that's become unbalanced, its balance factor hit +2 or -2, it triggers an automatic little shuffle, a rotation, to rearrange the nodes right there and snap the balance back into place. And these rotations are just brilliant. They somehow manage to fix the tree's balance without ever breaking that fundamental left is less than right rule. The whole point is to keep the tree short and bushy, which in turn guarantees that super fast dictionary-like performance that we wanted from the very beginning. It's a guaranteed win. So we have the simple but sometimes fragile BST, and we have the more complex but always reliable AVL tree. This brings us to a classic engineering dilemma. Which one do you actually use? It's not really about one being better, it's about understanding the trade-offs. Let's just lay it all out. A standard BST is way simpler to code, but you are taking a risk on that horrible worst-case performance. An AVL tree, on the other hand, is definitely more complex to implement. You've got to code all that balancing logic, but its worst-case speed is guaranteed to be fast. So if you know for a fact your data is going to be random, a BST might be totally fine. But if search speed is absolutely critical, or if there's any chance your data might show up already sorted, the AVL tree is by far the safer bet. So, what's the big takeaway here? It's that there is no single best data structure for everything. Understanding the strengths, the weaknesses, and the hidden flaws of each tool in your toolbox is what allows you to build smart, efficient, and truly reliable software. It's all about picking the right tool for the job you have to do. And that leaves us with one last thought that really goes beyond just code. This tension between the simple BST and the complex but perfectly balanced AVL tree, that's a universal design challenge. So I'll leave you with this question. In your own work, in your own projects, when do you choose the simpler solution that's just good enough? And when do you decide you have to invest the extra effort for that perfect, guaranteed result?